Hello, welcome back. Today we get to talk about vectors. So the ones in particular that we're going to talk about in this video are those in two-dimensional space. We will also see n-dimensional vectors today, but for now we'll stick with this. So a geometric description of a vector is a line in two-dimensional space, and well, more than a line, an arrow with its tail at the origin and its head at some particular point in space. So for example, we have this vector here that we'll call u. Similarly, we have one here that we'll call v. We can also have algebraic definitions of vectors, which tell us particularly the point where the tip of the arrow ends. So u in this case is the point 1, 2, v is the point -3, 5. We may also abstractly refer to vectors as just the letter with the arrow over it. Right? And we like to put the arrow over it because that distinguishes it from a scalar. Right. And from a matrix. A matrix is a capital letter. Right. A vector is a lowercase letter with a line over it, and a scalar is a lowercase letter without any embellishment. Alright, so what do we want to do with vectors? We want to be able to add them together. We are taking an algebra class after all. So how do we add two vectors? So let's go ahead and start with our same u and v, or at least approximate u and v. U is there, v is over here. We can at least pretend they're the same ones that were already drawn. And what do we do with them? Well, if we want to find u plus v, algebraically, I guess we can do that pretty easily in the way that we expect. 1, 2 plus -3, 5 should be -2, 7. So how do we do this geometrically? Well, let's get a little bit fancy here. So what we want to do is we want to take our v vector and we shift it sort of like this so that its tail is at the tip of u. So we're going to call this tail to tip. Alright, and let's unhighlight that, and then the sum of them would be the vector we get by pointing where the v's tip ends. Alright, so this blue vector here that I've just drawn, that's our u plus v, which ultimately you should get -2, 7. Alright, and then again, we could also write this abstractly by just saying this is the vector that is the sum of u and v. We could even write w equals u plus v. And then what else do we want to do? We've been doing it a lot, is scaling things. So we want to talk about what scalar multiplication looks like. Again, algebraically, we know what 2u should be. It should be 2 times 1, 2, which is 2, 4 by doubling each of the coordinates of u. And what we can find out is if we draw u again here, 2u is indeed in the same direction, and it's double the coordinates. So this is 2u. Right, so the x value is doubled, and the y value is doubled. Alright. To get negative values, so -u, -1 times u, would be just go in the opposite direction. Right. And then we can also do things like 1/2 u. Which we could compute each of these algebraically if we wanted. -1u should be -1, -2, and 1/2 u should be 1/2, 1. Right. And lastly, just for the sake of it, we can say that 2u is the vector labeled 2u, -1u, and 1/2 u. Are all the abstract versions of these. Now in our heads we should be thinking, just to point this out before we end, negative 1u, this here is the scaling by negative 1, versus if we just wrote negative u, this should remind us of the additive inverse. Okay, the thing where u plus minus u, minus u, which is not necessarily minus 1 times u, equals 0, the 0 vector. Alright, so that is our algebra with vectors in two-dimensional space. There should be a video about three-dimensional space as well, and I'm going to leave n-dimensional space for you to think about on your own. Alright, have a good one.